Mike. Check, check. And me, do you hear me? Sound check, check, check. Okay. Hmm? You can mute. I don't think. And where does your audio come out?
That's a great question. It's as far up. I paused it because they can't hear it. Oh, okay.
How about now?
Yeah.
No one to tell us no where to go. Say my
I understand. Okay.
Yes, go up there,
Got
turn
it.
off Wi-Fi.
Got it. Okay. Did that work?
And just see if you have to just give it. Don't do anything. Don't refresh. You might have to refresh and restart that. That doesn't matter.
Just hit play, right?
Try to restart the live stream, or don't restart the live stream. Just see if it's still playing. So
It's still going. It looks good.
that's live, and there's been no interruption.
Yep.
Melissa, can you see the live stream?
Yep.
Okay.
Should we go back to?
Well, I'll take it. This will probably clip me. Make sure I don't go red. Red. The quick brown fox jumped over the lazy brown dog. Take it down a little bit. Looked like we had just a tear on my D's. The quick brown fox jumped over the lazy brown dog. All good? Okay, I want to take over. I believe I must be source 2. I am. Okay. Are we live? We have good audio. We have good video. All right. Good morning, guys. Looks like we got a big fat glare on the screen on the live stream. House lights are off. Oops. Yeah. That's one way to get the glare to go away. Oops. That is not helping us. Well, that's already better. Oops. The question is, well, let's try to go farther back in the room. And bounce off the ceiling. Wow. How's that? No, that is not good. Let's try to go. Do I still have light on my face? Oops. Can you get the camera, get the thing out of there so I can see the... Sorry, guys. We are adjusting the lighting a bit because you may notice that we have a gigantic new screen. Maybe you don't notice because of the overall. I still look a little bit in shadow. So our key light needs to be. Goodness. We need to see what we can. Yeah. Yeah. I'm just trying to see where the main glare. Oh, it's coming from that probably. So we can just go maybe down in intensity a bit. Well, that's all the way off. So it's catching. Yeah, it's coming out of these things. Yeah, we usually try to go off the ceiling. That's not so bad there. You come down. Yeah, we'll quit screwing around. Yeah, lots of shadow here, but we'll live with it. Hey guys. So just giving you guys a few minutes to come into the room. We have the new live screen, and it's 80 freaking 6 inches, so it's really taking up the spare bedroom here. And we had to adjust our lighting so you can still see me to a certain extent and the board, but this doesn't look too bad. So we'll go with this and we'll play with it for tomorrow. So hope everybody is doing well, had a good weekend studying for the midterm. If I have to go backwards now, oh man. If I want to go backwards, there they are. I need these buttons. Okay, so we're going to do a little review today of what we've discussed so far in the classroom, and I thought I had more here on my screen, but sorry, we are completely disorganized this morning. Lighting, and there's different inputs to the machine, so we're not exactly sure what's going on. But for the midterm, we started around, we finished last time around the multi-electron orbitals. So we had multi-electron atoms to talk about, and that's where this exam material will mostly spend. We're going to give you a extra 30 minutes on the exam this evening, and again, it's same format. So you'll do the academic integrity statement at the beginning, and that means you are going to use only the material that we have for you. So you can use the equation sheet that we have for you. It has a periodic table and all the equations you could possibly need. We don't expect you to access any other source on the web. And in your on the computer you're using, we will use the B courses tracking software to see if you are staying on the page and in the exam to do the exam work. You are going to need probably scratch paper this time, or your tablet, or whatever you like to scribble on, because you will have to draw Lewis dot structures and things like that. It's not calculation intensive. You know, I don't like you to have to do calculations. I'd rather you do a conceptual, bigger, smaller orbital pictures so that you can show me you understand the concept rather than calculate a number. But there are numbers to calculate as well. But ranking things, in my mind, is better than getting an actual number. So we talked about atomic orbitals and filling up the atomic orbitals, and we used Hund's rule, and we used the Aufbau principle. We fill from the lowest energy shells to the upper energy shells. We use the Pauli exclusion principle, so we don't put more than one electron with exactly the same 4 quantum numbers in a orbital. And then we went across the periodic table and we looked at the various properties and electron configurations across the periodic table. So we developed electronic configurations for the various atoms, and we looked at their ionization energies and their electron affinities. So electron affinity was the energy released when an electron is added. So you forcibly add a electron to a neutral atom. So here I have neutral atom plus electron goes to the negatively charged atom. And I said forcefully add. Here's a chem quiz right off the top of the bat. I said forcefully add. Is that an apt description of electron affinity from what you can see here on the board? And I think the previous slide, going in reverse is going to be a hassle. How do I have my control buttons always visible down there? Stand by, guys. I'm going to try one more thing. How do I stop the slideshow? So probably in the settings here somewhere, slideshow, show play narrations. I don't want to do that. I don't use timings. Slideshow, show media controls. I got that on. Show without narration, presented by a speaker, show all the slides, advance them manually. Okay. I don't think I want to use presenter view. I'll try it on presenter view, but I don't remember which I had for primary monitor. That might help us because I can come over here, I think, and then do stuff like that. Okay. Sorry, again, we don't have the same touch controls here. Hopefully by Tuesday we will. The system arrived without all the features activated, so we're waiting for the company to help us activate all the features. But what you see here is the electron affinities and ionization energies. And if I just said to you, is it an apt description? Is it how you would describe electron affinity to force an electron onto a neutral atom? So start a chem quiz for us, Ryan, and it'll just be a yes/no, a yes/no chem quiz. So answer A if you agree. A is yes, force the electron on the atom is good, or B, no, you would use a different word. There's a different description for that. And this is semantic, so who knows? But just give me a quick count there. And when we have just 50 or 60 people or whoever's here already this morning, we'll have a look at what Ryan is thinking. We have to wait for Ryan's. Hopefully we don't have to wait for this every time. Ryan isn't ready. That'll go away in a minute. So we got about 6 people. Let's see what you're thinking. Is that an apt description? 65 people. Go ahead, Ryan. A lot of us are thinking no. About half of us are thinking no. Some are thinking yes. And this is not a good exam question because it is semantics. It's just a description of what your feeling is, I guess, on the whole system. This delay in switching sources is going to be a little annoying. Force, I don't think is the best word because these are all exothermic reactions. When you form the X- ion, you release energy. So in general, atoms, neutral atoms, are willing to, and again, we're using those semantic and hand-wavy words, are willing to accept an electron. And of course, you know me, I don't like to use the words willing, and I would say, I would draw you an energy level diagram, and I would say, how do I plot these two? That's a brilliant exam question. If I put the neutral atom and an electron here at this energy, where would you add the negative ion? And I hope you all would add the negative ion down here. It's just a relative energy, but we know there's a release in energy. These are negative delta E for all of these is negative. And if delta, I should use the other color because I will do that. I'll use the other color because we're using red for exothermic anyway, but they're negative. Delta E for all of those is less than 0. And that's the sign of an exothermic reaction. And that's a lower energy state. So the electron affinity, you go to a lower energy state. It always takes energy to ionize. So to pull an electron off, that always requires energy. So coming together of plus and a minus, you know that's going to go to a lower energy state. We talk about that all the time. As they approach, the energy of that state drops. We assign, another great exam question. What do we assign that energy to? And this is one of those that we actually assign this energy level 0 in energy. Again, there's no such thing as 0 in energy. That has some energy. They're moving around. They have thermal energy, blah, blah, blah. But in terms of the attraction energy, we assign that 0. The electron and the neutral species separated far in space. So I always harp on energy, and you should understand that that's going to be something that's not going to change. And through the whole course, you'll be answering questions on energy. So with that in mind, which of the following ions has the most negative electron affinity? So we have the chloride ion, the argon ion, and the potassium ion. And this is a variation of one we did in lecture already. So go ahead, we'll start a chem quiz, talk about that amongst yourselves. I think my system is virtually ready for me to join a breakout room. So I will. If when I do that, you can open display preferences again, your settings and displays, and you're mirroring. Why don't you make it? We hate to change anything at this point. show the results of the quiz. Okay, so oh, okay. Okay, I'll just go back and talk to them. Hi guys, I'm back. Sorry, still a few issues running the max back and forth. So we'll see what you're thinking here. I'll just tell you my thinking because we can't see yours right this second. So we want to know which of these had the highest ionization energy, and they are the highest electron affinity of these three. And what we can see here is that if you wanted to write the ionization energy, this is also going to drive me crazy. Why do I not see the yeah, how do I get it to stay down there? Oh, if I put the mouse on this, oh, maybe I have to have the mouse on this screen, but that doesn't help me. Sorry, guys. We are just trying to do, as usual, too much. Okay. So the question was, which of the following has the most negative electron affinity? So to which of these is it most favorable to add an electron? Which of these is most favorable to add an electron? Which has the most negative electron affinity, which drops the lowest in energy when an electron is added? So here we have the ionization energy expression written there, and we know those numbers for this system. The electron affinity is the reverse of that. That's when you add an electron to a species. So electron affinity is the reverse of that. And you can plot those across the periodic table. So the ion, chlorine, argon, or potassium, you can plot their relative ionization energies. And you know that that's going to increase across the periodic table and then drop with potassium. So argon, having the highest ionization energy, would have the lowest, most negative electron affinity. You have to take the opposite sign. So that's one of those things where you have to talk about energy and go through the whole thing in your head. What's positive energy? What direction, reaction am I talking about? And energy released or energy absorbed, positive energy versus negative energy. All those things are encapsulated there, as well as the periodic trend. So a good chem quiz to summarize all those things about periodic trends. So here is an atomic orbital that I've drawn on the board. Which of the ground state atoms, with that as its highest occupied orbital in the ground state, has the lowest ionization energy? So boron, chlorine, and aluminum are your options. We can show you a periodic table, maybe start the quiz. It might be easiest for me to just show you geez, little freaking wheeze. Show me the famous freaking, there it is. The famous touch bar fails us. So we'll show you the periodic table while you're doing that, so you have that information. Yeah, we'll try switching to your display. So we'll look at the result of, we're back. We'll look at the result of the chem quiz. And PowerPoint vanished. Okay, show me the result of the chem quiz. You still have that. So C is the most popular. And that is truly a annoying thing. That's not annoying. C is fine, but we are just having all kinds of trouble keeping the displays running. So let's go back and talk about this together. So I should be able to do that. Fairly easily there. So we were talking about which ground state atom with that as its highest occupied atomic orbital has the lowest ionization energy. So what kind of orbital is this? Well, I tried to draw an orbital that has a several nodes in it. So it has a positive node here. It has a negative node there, and then another positive, and then another negative node, lobe. So the waves function, and we've shown these in colors, characteristically. On the exam, we don't have colors. We'll just use dark and light colors for our changing sign of the wave function. So there's some kind of node here that's separating the causing that change in sign. And there's another node that's causing a change in sign here. So we have an angular orbital, an angular node and a radial node. Two total nodes that we can see. Two total nodes means we're in principal quantum level 3. And this has the characteristic 3p orbital shape. So we've identified N and L. So which of these has the p shell filled? Well, we can look at our periodic table. I may have to close the annotation to do that. We can look at our periodic table. Maybe. And we had the ions. You can't run PowerPoint at all. I need to, can I see it? PowerPoint. Right, the slide that we're on, current slide, that one. So the atoms of interest were boron and carbon and aluminum. Carbon and aluminum. Chlorine and aluminum. Sorry about that. It is boron, chlorine, and aluminum. So those in their ground state, which has the lowest ionization energy. So ground state boron would be a 2s orbital. So that guy's out of there altogether. Aluminum and chlorine both have 3p orbitals filled. Aluminum has 1 and chlorine has 6 electrons in its 5 electrons in its 3p orbital. And as we know, the ionization energy, as you go across a row in the periodic table, ionization energy generally increases. It goes I didn't do a very good across the row there. Going across a row on a periodic table, the ionization energy generally increases. So chlorine you would expect to have a higher ionization energy than aluminum. So we can say that the lowest ionization energy is, the lowest, criminy. The lowest ionization energy of those is, we had with that filled orbital, is the aluminum. So I don't have one of my famous boxes there. So we'll just do that. Okay. So here is another one. We did this one in class. This shows us the effective nuclear charge. So I'll just walk you through this. Here are three species, two of them ions. All of them, they're all have p orbitals as their highest occupied state. They're all not in their ground state. They're all in excited states. And each of them have a effective nuclear charge of around 1. So we have a single positive charge for hydrogen, 1 proton. There are 2 protons here in the nucleus, but there's the 1s electron. So here we have Z effective is around 1. And lithium, 3 positive charges in the nucleus, but it has an electron. It's doubly ionized, an electron here. So its effective nuclear charge is +2. So the electrons at the highest, farthest away from the nucleus, experience an effective nuclear charge of +2. This electron experiences an effective nuclear charge of +1, and this one experiences a nuclear charge of +2. There's not any shielding of electrons involved there. There's only 1 electron. So we can do that calculation, and we did that calculation last time. And we used the general expression for the energy, ionization energy of single electron species. And we used the effective nuclear charge as 1 for all of them, because the s electrons were shielding the p electrons in this case. And we saw that the largest, the smallest is what I asked for, I guess, was hydrogen in the 2p ionization energy. So here, I just whipped this up this morning. So let's hope not only having completely new systems and software, that I also was not so groggy this morning that this makes no sense. Which neutral atom with the occupied orbital shown, so we've already gone through that kind of thing, so we know that is a 3p orbital. So which neutral atom with the occupied orbital shown as its highest energy electron has the photoelectron plot shown here in red, plot number 2. So think about that for a second. And I will try this time to hop into a breakout room. Okay, I'm back. We'll talk to the group. This is very similar to the last one, so we can cover some of those last topics. I know there sounded like there was some confusion on the last one in the live stream chat. So hydrogen, lithium, and aluminum. Again, we kind of want to know which has a high ionization energy. A high ionization energy because this plot, this photoelectron plot, the minimum photon energy that will ionize it is here. So these two species below that have a lower ionization energy. So we need a high ionization energy out of these. And we have, we can look at the periodic table at hydrogen, lithium, and aluminum. Hopefully. So we're going to look at hydrogen, lithium, and aluminum. If hydrogen and lithium are in that state, they are excited states, and they have lithium and hydrogen are excited states and effective nuclear charge around 1, because there's 2 electrons here in the lithium in its excited state, and hydrogen has just 1 electron. So not only effective nuclear charge, the nuclear charge the electron sees is 1, and they're in this excited state up here where aluminum is. So then we have to say, well, I'm going to go across the periodic table and down. Lithium in the 3 state with 2 positive charge, with a +1 positive charge seen by the electron, has a, compared to aluminum, with the full complement of its 13 electrons. So this is one of those things where you say, is aluminum the, does it see its outer electron see more or less than an effective nuclear charge of 1? And there's a lot of shielding going on there, but there's 13 positive charges. So it's probably not 100% shielded, that outer electron. It's likely it sees a little more than the positive charge of 1 here. So the total positive charge that outer aluminum experiences is higher than the hydrogen and the lithium in that same orbital. These guys see the full +1. These guys probably see more than +1. So a higher ionization energy for the lithium and the aluminum. So you're looking at hydrogen, and hydrogen has a 3p electron. Lithium has its 1s 2 and 2s1 normally, but that s1 is, now I'm just forgetting how to use the board overall. Hydrogen in its 1s state is promoted to hydrogen in the 3p state, so that's an excited state, and the effective nuclear charge is very close to, in this case, exactly 1. Let's not even call it an effective nuclear charge, call it a nuclear charge of 1. The lithium has 3 electrons. The 1s2 2s2, 2s1. So 1s2, 2s1 is promoted to, by absorbing a photon, lithium in the 1s2, 3p1 state. It's an excited state. It absorbed a photon to do that. And here, the effective nuclear charge is very close to 1. These two s electrons are very effective shielders of the outer electron there. In aluminum, you have all these p electrons. So aluminum, we have its electron configuration is the same thing as sodium. So I'll just write it out. 1s2, 2s2. I have to get to 11 electrons. 2p6, that's 10. 3s1 is sodium. 3s2 is magnesium. And aluminum is 3s2, 3p1. So its first p orbital, it's aluminum in its ground state here. Now, you have to say, what is the overall shielding of that? Is if it were effective nuclear charge around 1, then all of these would have very similar ionization energies. But p electrons are not particularly good shielders of the nuclear charge. And as you go farther out, the electrons are not as good shielders of nuclear charge. So it's likely that this electron here, with these plus 13 nuclear charges here, it's very likely that that Z effective is greater than 1. So that would have the highest ionization energy of those three, the greatest nuclear charge effectively on that electron. So you're looking at electrons that are shielding. These electrons are shielding. These s electrons, very effective shielders, no shielding there. These electrons are relatively effective at shielding, but there's 13 pluses, and in particular, the p electrons below this p are not particularly effective at shielding the nuclear charge. So you have an electron there that probably has a effective nuclear charge, you could argue, greater than 1. And again, this is an argument. It's the kind of argument that you should follow. There's no argument this complicated on the midterm exam. We're doing some significantly more complicated argument to follow here on this particular question to give you an idea of what shielding really is. And this outer electron feeling a charge of more than +1, but much less than +13. So it's between those two, and likely bigger than both of those. Gives it a higher ionization energy. Okay, so that kind of explains, again, the one prior to that as well. So we won't go back and look at that one in particular. And we've already talked about things that look like this. So this ionization energy, this one we said had the had aluminum as the highest ionization energy there because its effective nuclear charge on that 3p electron was the highest. And we talked about effective nuclear charges here for those three species. And we did that one in class. So we went from there to bonding and we talked about ionic and covalent bonding and Lewis structures. So from our Lewis structures, we talked about bonding and formal charge, resonance structures, and oxidation number. So the double ionization process here, we talked about this one in, oh no, we talked about something like this in class. For the double ionization process, what's the change in the bond angle and the bond order? So I have NO2 minus, I take away 2 electrons, that's double ionization. When I take away 2 electrons, what happens to the bond angle and the bond order? Let's just concentrate on the bond angle to start with, and start a quiz for us there, Ryan. And we'll let you guys talk about that for a second. So take a minute, as if you're doing the exam, jot down the Lewis dot structures, nitrogen, the central atom, and see what you come up with. To you, we should see that slide. In fact, go back one. And hopefully you can drag the cloud or the clicker cloud over there. Okay, guys, we're back. We're still fuddling with our setup. So it got closed maybe when we switched to presenter view. When does it get? I'll switch to you and see what we see. Hopefully we see your PowerPoint because you're in presenter mode. We do not. Well, but we don't, you don't see presenter mode, which I don't get. Okay, so we're back. We accidentally closed the clicker quiz in our attempt to make this smooth, which we are failing spectacularly at doing. Let's see what 62 of you are thinking. Increases is the most popular. So I think I agree with increases. Let's see what I have worked out for you. So the double ionization process, the bond angle. So you have to write the Lewis dot structure. So nitrogen and two oxygens. So you have to take the valence electrons for oxygen, and there's 6 of those. The valence electrons for nitrogen, 5 of those. So 6 and 6 is 12, and 5 is 17, plus 1 more gives you 18 electrons. And you can write that in this electron configuration there. And you would say in this electronic configuration here, I would have a bent configuration. Take away 2 electrons. Take away 2 electrons, and I look like a carbon dioxide molecule. The best Lewis dot structure there, isoelectronic with carbon dioxide, a 16 electron species. Linear is the better expression there. So indeed, an increase in the bond angle. So other things to think about here, you could ask yourself, what is the hybridization around the nitrogen there? Nitrogen has to accommodate 2 things, steric number 2. Steric number 2, it should be linear with sp sp hybrid orbitals. I can write some of that down. So the nitrogen will hybridize, use its sp hybrid orbitals. So it'll form an sp orbital in that direction, an sp orbital in this direction. And now I'm only drawing the positive part of the sp. The oxygen, what's the hybridization on the oxygen? Well, its steric number is 1, 2 for each of the electron pairs, 3 adding the nitrogen. So it has steric number 3. The oxygen will sp2 hybridize. So there'll be a sp2 hybrid on the oxygen to form the sigma bond. It will have the lone pairs in the other 2 SPs. That bond angle, these bond angles, less than 120 degrees because it's electrons and a bond. We don't generally even talk about bond angles when we're talking about unpaired electrons. We ignore them entirely. There's one more bond, so that's a sigma bond. So I would say this sigma bond is an sp on the nitrogen overlapping with an sp2 on the oxygen. And of course, you would take the plus and the minus combination. You'd form the bonding and the anti-bonding sigma orbital. There's also a pi bond, and the pi bond would be formed from the leftover p orbitals. Oxygen has only 1 p orbital left over because it used s and 2 p's. And nitrogen has 2 p orbitals left over, and it can use one of those to form a pi bond with oxygen. Question?
How do you know how many pi bonds and sigma bonds are in a molecule?
The question is, how do I know how many sigma and pi bonds there are in an orbital, in a molecule? And we use, that isn't generally an easy question to answer. The first bond you form between 2 atoms is a sigma bond. All the rest have to be pi bonds. So we'll talk about the highest energy molecular orbitals, the valence molecular orbitals, and we will count just those in our bonding. The first bond is a sigma bond. The second, third bonds are pi bonds. So I can count those out very simply. And so a sigma bond, a sigma and a pi, a sigma and a pi, and a sigma and a pi. So that's a lot of information around that. Let's, but that's a lot of the information you need for the exam as well. So increase there. And we could tell that from the shapes. Let's look at this guy here, which is also, we're going to do electron dot structures and bonding and VSEPR shapes. But let's talk about the oxidation number for this one. So we have two reactions, nitrogen and oxygen forming the +2, nitrogen and oxygen forming the -2. And these, I hope you recognize. That is NO2 minus and NO2 plus. You just drew those Lewis dot structures. So I'm not doing anything very new here. So I want to talk about the oxidation number on oxygen going from the atomic, the dimolecular oxygen gas to NO2 plus or to NO2 minus. But let's just talk about condition one. I go from oxygen gas to oxygen bonded to that nitrogen in NO2. So you've already got the Lewis dot structures. You've drawn them out. Talked about the bond angle. We even had formal charges on that last slide. Let's talk about our oxidation numbers. We got a quiz going. Okay, we're back. You've had your Lewis dot structures drawn, so we'll see what you're thinking. We'll roll the dice and go over to Ryan's computer, and hopefully we will see. Oh my goodness, we are completely across the board on this. Oxidation numbers, they are such a thorn in everyone's side. I might be able to bring up our discussion of oxidation numbers, maybe. Stand by. Yes, I believe I can. So we'll go back to my source. So we talked about both formal charges and oxidation numbers and how to count them. And NO2, our favorite molecule, we've been going through the entire series of lectures looking at NO2. And formal charge and oxidation number are simply accounting practices. When you do a formal charge, you share all the bonding electrons equally between the two atoms you're trying to calculate a charge for. So it's very egalitarian or covalent sharing. Here we have an oxidation number calculation. You do the same thing. You draw the Lewis dot structure. And when you're assigning the electrons to the individual atoms, for the sake of calculating oxidation number, you don't assign them for any other reason except to calculate formal charges and oxidation numbers. We assign them ionically. We assign them to the more electronegative element. So if you assign all 6 of those electrons to oxygen, then that, all 8 of them, 2, 4, 6, 8, there's 4 in the double bond, and there's 2 lone pairs. So 8 electrons to the oxygen. Oxygen, then you compare to the atom, the neutral atom, and we do the same thing if it were a formal charge, but we divide up the electrons differently by sharing. Here we don't share. Compare those two numbers. Oxygen in this molecule, if we do this accounting, appears to have 2 additional electrons compared to its atom. 2 additional electrons would give it a -2 charge, and we call that the oxidation number. The nitrogen, +3. So the nitrogen is a +3 oxidation state relative to its atomic state. The oxidation numbers and the formal charges should all add up to the charge on the molecule. Just a different way of distributing electrons. So now I'm looking at the very tiny display on my magic bar here. And we will go back here to the oxidation numbers. So let's look at those. So nitrogen and oxygen, their oxidation numbers as diatomic molecules. I think you would probably guess that the oxidation number of oxygen as oxygen molecules is 0. There's 2 of them. They've got to share everything equally. That's the bond order. We're going to do both of them, so we'll do the bond order as well. Bond order 2 from that Lewis structure of oxygen. Bond order in oxygen over there, also 2. So no change in the bond order in that reaction. The oxidation number, 0. So you have the case where they're identical atoms, and if they're identical atoms, there is no way to divide this guy to some of them to the more electronegative element. So you have to divide them equally. Elements in their standard states have oxidation number 0. You can take that one to the bank. When they form molecules, they're going to have an oxidation number. So oxidation number for oxygen, we just worked through that, is -2 in that species there. It's also -2 in the neutral ion, or the negative ion. So the bond order stayed the same. the oxidation number decreased. You can do that same argument for NO2 minus. NO2 minus, you have an extra electron, and we looked at that one already. The oxidation number and the bond order. The bond order decreases. So here we have a resonance situation. So the bond NO bond order is a mixture of a double and a single bond. So if a bond order of 1.5, that's a decrease in the bond order. The oxidation number stays 2. So that's also a decrease in the oxidation number. Question?
Can you review what bond order is?
The question is, can we review what bond order is? And we're going to do bond order in 2 ways. We're going to be able to look at a Lewis dot structure. And if all I give you is a Lewis dot structure, please look at the Lewis dot structure and count the number of bonds. Bond order 2, 1 sigma 1 pi. If you have a resonance structure, as you do here, so that double bond could be on this oxygen or that oxygen. So in effect, that double bond is shared equally between those 2 oxygens. So each has a sigma bond, and it has that to itself, bond order 1, and then it shares the double bond via the resonance, the moving of that double bond around the resonance structures. So 1 full single and half of a double gave you bond order 1.5. When we did our molecular orbital theory, we also came to those numbers, but it was more obvious because we looked at bonding and anti-bonding orbitals. And we saw our anti-bonding orbitals canceling some of the bonding orbitals so that we could calculate a bond order from molecular orbitals as well. And I think if we go on here, we'll actually do something like that. So let's try to do that. We'll do a VSEPR kind of question here first. So which of the molecules or ions below have a shape similar to PCl3? So phosphorus trichloride. So draw the Lewis dot structure for PCl3, come up with a VSEPR shape, and see how similar it is to these. And you might want to think about total number of valence electrons for each of these to make your calculations as easy as possible. And let me know what you're thinking. Okay, let's come back together here as a group. We'll look at hopefully what Ryan has to show us in terms of a quiz here, and it looks like most popular is H3 S plus of those. So I will jump back. That is a long time to have to wait for that switch. So you can probably arrange it not to show all that feedback. So I need to draw Lewis dot structure, and here I haven't drawn all the electrons. There's lone pairs on the chlorine atoms, but it allows me to say that phosphorus has to accommodate 1 chlorine, 2 chlorines, 3 chlorines, and a lone pair. So it has to accommodate 4 things, steric number 4. So nominally, with steric number 4, these bond angles are 109, 109D, 109.5. If this is a lone pair, then we don't count that bond angle. We count the bond angles between actual bound atoms. But with that lone pair there, squashing its electron density down near the central atom, this bond angle is less than 109.5. I don't know. I've drawn everything wrong. Everything possibly I could draw wrong there. I've drawn wrong. So that bond angle here is less than 109.5. And indeed, it's around 107 degrees. I'm not concerned that you know 107. I just concerned that you know it's less than 109. So we can look through the rest of these. We'd call that trigonal pyramidal. It looks like a little trigonal pyramid when it doesn't look tetrahedral. Its VSEPR arrangement is tetrahedral, but the shape of the molecule, we ignore the lone pairs and rename it as trigonal pyramidal. And SH4, as you correctly predicted, has also steric number 4 with a lone pair of electrons. Silicon trichloride, steric number 3, does not have a lone pair of electrons. And ICl3 has 2 lone pairs of electrons. So we'd have the shape match here. We would have this shape be trigonal planar, that shape be a bent T shape. So similar shape as you predicted, that sulfide molecule. So we went on to talk about the actual quantum mechanics of the molecular orbitals, everybody's favorite topic. And on the exam, they're all pictures. On the exam, they're either filling your molecular orbital diagrams, which I give you, or you are looking at the overlap of the bonds. And we said the internuclear axis is the positive Z axis. When the positive Z axis overlaps, you would have a positive here overlapping with a negative here. So positive Z axis for both of them, you would make a sigma star because you'd have constructive and destructive interference. The sigma is created by the flipping the phase of those, and you flip the phase of those to form the sigma bonding orbital from p orbitals in this case. You can form sigma bonds from p orbitals. You don't have to have only pi orbitals. And we looked at the filling of the various structures, pi bonding versus sigma bonding. We saw how a little bit about how the ordering of the pi and sigma orbitals vary across the periodic table, but you do not have to know about that. I will give you the actual molecular orbital diagram as I do here. And I can ask you things like which paramedic species has the weakest chemical bond. So we'll just go through this one. Here I have gone from the molecular orbital energy level diagram, and I filled it. And fluorine, how many valence electrons in fluorine? Fluorine's all the way on the side of the periodic table with 6 p electrons. So it has 2s and 5 p electrons. 7 valence electrons in the p shell for fluorine. The principal quantum level 2 for fluorine. So let me just write it down because I'm clearly delirious in everything I say today. So fluorine has 1s2, 2s2, 2p5 as its electron configuration in the atom. All 7 of those valence electrons should participate in molecular orbitals. I have an s and 3p atomic orbitals on each fluorine. So the number of orbitals I have are an s, a p, and a p, and a p on one fluorine, and an s, a p, a p, and a p on the other fluorine. All of these atomic orbitals add to form molecular orbitals, and I better form 1, 2, 3, 4, 5, 6, 7, 8 molecular orbitals from those 8 atomic orbitals. And those are these atomic orbitals here, 1, 2, 3, 4, 5, 6, 7, 8, with the designation sigma and sigma star, pi and pi star. Star is the anti-bonding molecular orbital. And then I just have to fill with electrons. So these are all the kind of things you need to know. I have 2 fluorines, each bringing 7 electrons. So the other fluorine has this same electronic structure. So I'll just draw that again up here. Fluorine 1 and fluorine 2, 1s2, 2s2, 2p 2, 2p 2, 2p1, 1s2, 2s2, 2p2, 2p2, 2p1. Those are the atoms. I have to use 2, 4, 6, 7. These 7 valence electrons from each fluorine to fill my molecular orbitals. How many molecular orbitals will I have? I will have, let's do it the other way. I will have those 4 molecular atomic orbitals from each atom. So I'll have 8 molecular orbitals. And I will have to add to those 14 electrons. So there are the 8. And as I said, I'll give you that order. Your job is just to put in 14. In F2, you'll be deficient by 1 electron. It has a positive charge. F2 minus, you'll add 1 electron. So 13 electrons there, 15 electrons there, 14, 15, 16 electrons there. So I think I've drawn that out for you. Here are those electrons filled into that molecular orbital structure. And you want to look at the bond order for strength of bond. So you have these guys, sigma and sigma star, that more or less does not contribute to your bond order. There's the same number of antibonding and bonding electrons. So you go up to your P's and you can add now. I have, in this case, 2, 4, 6 bonding electrons, and I have 1, 2, 3 antibonding electrons. The difference between those is 3. And I have to divide that by the number of bonds that I have in fluorine. And fluorine is a single bonded species. So this, I can just divide it by 2. 3 divided by 2. Don't worry about the single bonded species for fluorine. Calculate your bonding electrons minus your antibonding electrons and just divide by 2 because 2 is the number of electrons it takes to make a bond. So that bond order is 1.5. And then it's kind of easy to get the rest because you add 2 more electrons. They are both antibonding electrons. So you have the same 6 bonding and 2 more antibonding. So now your bond order is going to go down to 0.5. So these 6 help you bond. These 5 don't help you bond. So a triple bond order 3 from these sigmas, but a bond order 2.5, anti-bond order of 2.5 gives you a total bond order of 0.5. And here even gets worse. You add another electron. So you go down to bond order 0 here, where I had 6 bonding electrons and I had 6 antibonding electrons, sigma stars and pi stars. So that has bond order 0. So strongest bond, highest bond order. Here I have a extra electron, lower bond order there, and 2 extra electrons. We wouldn't expect F2 minus the ion to exist. You put 1 electron on, it gets a little less stable, accepting 2 electrons, and you'd break into 2 fluorine minus ions, atomic ions. Okay, so we're out of our time that we have normally. I can hang out here and answer a few questions if there are any, and or we could do another couple more of these practice chem quizzes. It looks like I got a couple more in the bank there. What do you guys want to do? There were thousands of questions, says Melissa. So let's start there, maybe. The first chem quiz was the electron affinity.
Actually, no, I think Ryan, was it the one about like calculating ionization energy of like
Yeah, that we did essentially go over that one twice already because we did the same kind of chem quiz twice.
If we can, I'd like to continue answering these.
People want to keep doing more chem quizzes. Are there any? So I'm sorry, guys. We're all talking together, the student instructors and I. It seems like there were questions early on about those ions and the effective nuclear charge. And we did go back and look at, there were 2 in a row that we did the same kind of argument. Let me just tell you this. Every electron in the entire atom has an effective nuclear charge. There might be 13 positive charges, but no electron really sees all 13 pluses of those. The s electrons, the 1s electrons, see closest to plus 13. They're the lowest energy, and that's why. They're really close to the nucleus. They see those positive 13 charges. As you move away, that nuclear charge decreases, effective nuclear charge decreases, and it never really goes to 0. As you go out, you add 1 more electron to the atom, and that helps shield 1 more positive charge. So your effective nuclear charge drops off as you go out in a principal quantum level. So when we looked at something like fluorine, we were just looking at it. So fluorine, 1s2, 2s2, 2p5. What are the effective nuclear charges? We have 7 positive charges in the nucleus. Fluorine, atomic number 7, 7 protons in the nucleus. These 2 electrons have experienced very close to those plus 7 nuclear charges. Electrons in the same shell don't shield each other very well. In the same L don't shield each other very well. So there's each of those sees something like plus 7. You could say each of those has the same effective nuclear charge, something slightly less than 7. These guys here, these S do a pretty good job of shielding the nuclear charge. So these S electrons, the 1s, effectively shield the 2s pretty well. So these guys are seeing closer to plus 5 in their effective nuclear charge. So the s electrons, pretty good shielders of, especially the 1s, they're very close to the nucleus. So these plus 5-ish. So if you had to say something, you would say, we never ask you for an exact number, but you'd say the effective nuclear charge is something less than plus 7 and probably a little greater than plus 5 because you don't get complete shielding. So in there, somewhere in there is the effective nuclear charge. When you get out to the p electrons, each of those p electrons feels a effective nuclear charge that's about the same. The p electrons don't shield each other very well at all. And since they don't shield each other very well at all, that was the origin of the ionization energy increasing as you go across the periodic table. These guys don't shield each other very well. So more p electrons are still seeing about the same charge. So all of these guys here, they're shielded by another couple s's. So now we're seeing something like +3 out here, but they're all seeing about +3 out there. And again, less than +3, probably because of the shielding, is, I'm sorry, not less than +3, something like +3 because you have s electron shielding, 4 of the s electron shielding. They don't shield them perfectly. It's probably a little bigger than +3 because it's not perfect shielding. But each of them about the same. So any electron you pull off sees something a little larger than +3 effective nuclear charge. If you went one more element over to neon, then you'd add another electron, another proton to the nucleus, and another electron in about the same region of space and in a p area where they don't shield each other very well. So 2p6 with 8 electrons, these guys, that extra nuclear charge, they feel almost all of that. So these guys feel much closer to +4. They have the same 2s and 1s electrons shielding them. So these 4 minuses help shield some of those +8. They do a pretty good job. So this will be a little bigger than +4, but it's a whole +1 bigger than the fluorine. And that whole +1 bigger than the fluorine is why you had that increase in ionization energy going across the periodic table. Okay, so that's that. So the other request is just maybe do another chem quiz. Is that the next thing people would kind of want to do, or is there another specific question? I'm surprised you want to see them. The absolute we're having such poor success in discussing them because of the technology, and I get so flustered with the technology. I'm interested in going back to look at how many things I might have just said wrong, unfortunately, with the thing of the technology and the work at the same time. No, I don't want to do that. I want to do that. I noticed myself fumbling, and I hope I corrected myself through most of the fumbles. So let me see about the ones that I have left, and let me see what's maybe most relevant for the midterm tomorrow. Tonight, midterm tonight at 6 p.m. Pacific time, and tomorrow morning at 6 a.m. Pacific time for the people in Europe or other places. Oh, I like these two. Ooh, neato. Let's do that. Woohoo, yippee. How many carbon p orbitals are used in this entire molecule to form pi bonds? Wow, scratch that out for a second. And I'll scratch it out for a second. The Lewis dot structure is here, so you don't have to do anything fancy. Think about sigma and pi orbitals there. Okay, so you're spending a little time thinking about this. I'll give you some hints and let you think a little bit more. So kind of listen from one ear. Pi bonds are formed above and below the internuclear axis. They form after the sigma bond. You form a sigma bond first and then your pi bonds. If you form a double bond, one of them has to be pi. The first one has to be sigma. So you can count straight away the number of pi bonds in that molecule. Doesn't really matter if there's resonance going on. In this case, actually isn't. So you can count them straight away. The question is, how many p orbitals? So think about that a little bit more, and we will see what the vote shows us. Okay, let me give you my thinking there. Don't think I have to do any of those things. We can see. Oh, Ryan can tell you what the vote is. I mean, I could technically run iCloud here and save all this switching. Real popular for 6. And I think it probably got real popular for 6 after I said there were 3 pi bonds. I didn't look before then, but I agree if you have to form some pi bonds. I have carbons 1, 2, 3, 4, 5, 6, 7. And I have to form a pi bond there, a pi bond there, and a pi bond there. Then carbons 1 through 4, 6, and 7 are sp2 hybridized. So carbons 1, 2, 3, and 4, you should be able to just follow me along very quickly there. There's no lone pairs anywhere. So you can immediately say that carbon is sp2 hybridized. Why? It has steric number 3. This guy has steric number 3. That guy, steric number 3. That guy, steric number 3. That guy, steric number 3. 1 through 4 and 6 and 7 all are sp2 hybridized. Well, you can see why there's no way in the world I should ever be allowed to actually write on the board. I'm just miserable at writing. So that's why we use PowerPoint. The other reason we use PowerPoint, obviously, it's a beautiful canvas to write upon, and it's clear, and we can give you it all in advance as well. So they're sp hybridized. So this one, this one, this one, this one, this one, and this one are all sp hybridized, sp2 hybridized. That means each one of these, its atomic orbitals look like sp2, 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 3 hybrid orbitals, and the p orbital left over. And remember, this 2 here isn't electrons. It's the name of the hybrid orbital. So I have these 3 hybrid orbitals and this 1 left over atomic orbital. Hybrid orbitals and atomic orbitals are all atomic orbitals, but these are mixed up in a non-standard way, so we call them hybrids. Each one of these has a p orbital left over. And those p orbitals will all form pi and pi star molecular orbitals. I did what? Ah, yes, thank you very much. Someone is awake and saying I'm really messing up there. With this special pen, I can just flip it over and it becomes an eraser. Ooh. I still should change. Someone caught that I was writing 2 there instead of S. So sp2, in this case, they're carbon, so they are 2 Ps. And I found then that I had 1, this guy, that p orbital, 2, that p orbital, 3, that p orbital, 4, that p orbital, 5, and that p orbital, 6 available to form my pi bonding system. That guy there, sp3 hybridized, steric number 4. No p orbitals left over to form an sp, a pi bond. Okay, neato. How about this? There are pictures on the midterm, kind of like this, pluses and minuses. What do? So formaldehyde is planar, CH2O, which best describes the pi electron density. So pi electron density, the pi molecular orbital around, or molecular orbitals around formaldehyde. Think about that for a second, and we'll see what you're thinking. I'll walk you through this one. You can just show me the vote over there, Ryan. Only 20 of you voted. You're spread out A, B, C. Anyway, C is slightly more popular, but hardly statistically significant. So A, B, C orbitals, or A, B, C answers about the same. So if you looked at this Lewis dot structure, remarkably, it is planar. Carbon is sp2 hybridized. So it looks like a 120 degree bond angles on that. So every bond angle is 120 degrees. And I've drawn that in the plane now, where the hydrogen oxygen and hydrogen oxygen bond angles are 120, and the hydrogen hydrogen bond angle 120 degrees, all of them equal. That gives you a planar molecule. So I think I have an animation of the planar molecule. There's the plane of the molecule. Now you have the p orbital left to form. So you have, excuse me, the pi orbital left to form. you formed the sigma bond, and that sigma bond was formed. Oops, boy, that goes fast. The sigma bond here, Lord have mercy. I might be able to. Ooh, look at that. I can keep my annotations up and do my animations if I'm going from computer to computer. This bond here is formed from an sp2 on the carbon. This oxygen has to accommodate those 3 electrons, or those 2 pairs of electrons, and that. So the bond is formed from an sp2 on the oxygen as well. So you'd form a molecular orbital from the combination of those 2, a sigma and a sigma antibonding orbital. You have the p orbital left over. And as you know, the p orbital left over will be perpendicular to the plane. So the p orbital for carbon and oxygen look like that. And that's going to form your molecular orbital, your pi molecular orbital. And that is going to be above and below that plane. And we do have an animation there that will look better than my drawings to show you that that is above and below the plane. Okay, so that's a good description. We didn't do any ideal gas law questions. Here's a simple ideal gas law, and on the exam, you are asked to calculate pressures and partial pressures of a system. Oh, we already did that one. That's a boring one. Oh, well, heck. I thought I had an interesting one in there. I guess I don't. Oh, you have it. Well, let's just show yours. We'll just, I'll just walk you through a quick, very quick ideal gas law expression. So I have a 10-gram sample of carbon dioxide solid, cram it in a balloon. The total balloon volume that it can expand to is 2 liters. Beyond that, it'll pop. So when the balloon is warmed to room temperature, will the balloon pop? Yes or no, or you can't tell. So I go from dry ice temperature, maybe. Solid dry ice is minus 70 Fahrenheit, or 60 or 70 Celsius, I think, or Fahrenheit. I think it's C, minus 40 C. I can't remember. It's cold, much colder than frozen, much colder than wet ice. Oh, that must be C. So it's around minus 70 Celsius. So 70 degrees lower than wet ice. So you can keep things much colder in dry ice than wet ice. And it sublimes directly into the gas phase. So it also doesn't fill up your cooler with water. So you have dry ice solid. You let it sublime to dry ice gas. The question is, will it explode a 2-liter balloon? It's actually pretty similar kind of to the exam question in a certain extent. So we have 10 grams of carbon dioxide. How many moles of carbon dioxide is that? We know we do this molar mass all the time. Carbon dioxide around 45. 10-gram sample, so it's around 1/4 of a mole of carbon dioxide, solid. Quarter of a mole of carbon dioxide at room temperature, quarter a mole of gas. Well, 1 mole of gas at room temperature is 22 liters. A quarter of that is around 5 liters. So that would break a 2-liter balloon when all that 10 grams or about a quarter of a mole of carbon dioxide is allowed to expand to the gas phase. Okay. So that'll wrap it up, unless there's something urgent coming in on the live stream chat, and we will release the midterms this afternoon at 6 p.m. You have 90 minutes to complete them. There's 40 questions, I think. Okay, the midterms, we're going to go, we've got all the questions. We're just going to group them into the various versions right now. And we will post them as soon as we're done with that. So you'll be able to see them. You won't be able to take them. You won't be able to click on them until 6 p.m. But you can check that you've been assigned the proper time. So DSP people will have the extra time. The people will be assigned to 6 p.m. tonight and 6 a.m. tomorrow. So you can check those things this afternoon, probably by noon. Okay. And we will. I just hate that.